Hello everyone, welcome to Davig Griffiths Electrodynamics. This is problem 3.36. So, from the book, it says, show that the electric field of a perfect dipole given by equation 3.103, which is found somewhere. This equation here. Show that equation can be written in a coordinate-free form, meaning there's no reference to, specific variables, coordinate system variables like r, theta, or phi, or x, y, z, but just in terms of these sort of vector expressions. So that's why they call it a coordinate-free form. But basically, we need to somehow show that this can be written like that. So let's try to figure that out. So I did go ahead and write down the expression that we're starting with, and now we need to somehow derive that other expression. So, given a pure dipole situated along the z-axis, and if you have some point, that you're trying to find, the potential or electric field at, I just kind of drew a setup that hey, you have a dipole here, you have some point that maybe you're trying to find the electric field at. And I drew the r hat, and this is the theta hat unit vectors there, and then I drew the angle between the dipole moment and our vector r as theta. So anyways, our dipole moment can be written like this in terms of its vector components, right? There's not going to be a phi component to our dipole moment, just an r and a theta component. There's no theta component to our electric field. Our dipole moment should only have an r and theta component. It's axially symmetric. If you rotate a pure dipole like this, it doesn't change anything. But if you rotate it like this or change which direction it's pointing, I guess that does change things. So this is, we can just kind of generically express our vector like this. We have an r hat, our r and a theta component. But we can rewrite these r and theta components as p dot r hat plus p dot theta hat. So when you take the dot product between a vector and the unit vector, that's just giving you the projection of that vector on that axis. So it's giving us the p dot r hat is p sub r and p dot theta hat is p sub theta. These terms are the projections of the vector p onto those unit vector directions. So we can kind of suggestively write it like this. And then p dot r hat is just p z hat, because the dipole moment is situated along the z direction, and r hat, so we just have to take the dot product between z hat and r hat, which is just p cosine of theta. And again, if you're not familiar with how the spherical unit vectors are expressed in terms of Cartesian unit vectors, use this spot in the book. R hat can be written in terms of x, y, z hat like this. And so r hat dot z hat just gives us this cosine theta term. If you really don't know how those are derived, there's plenty of videos and things on YouTube that you can look up to show how all that's derived, but I'm just going to use that fact. So p dot r hat is just p cosine of theta, and then p dot theta hat, just using that similar thing from the book, is minus sine of theta. So we get p times minus sine of theta here. So then we can plug in these two expressions into this vector expression, and we get p is equal to p cosine theta r hat minus p sine of theta theta hat. And then I do pre-calculate this expression for theta hat, because if you look at the expression here for the electric field, what we end up doing is trying to somehow eliminate these theta hat and r hat terms. So when you plug in, well, let me think here. So let me think here. So we have this expression, and we figured out these sort of expressions here, and we can derive an expression for theta hat as cosine of theta. So you can add this to the other side and subtract p to the other side, and then the p's cancel out, so you get cos theta, I guess cos theta r hat, I forgot that, minus p over sine of theta is theta hat. And then if you plug theta hat into this expression, which I did forget an r hat here. Let me plug that back in. So if you plug this expression for phi hat into the electric field expression, we have the sine of theta here. Everything else stays the same, but we have the sine of theta times cosine of theta minus p over sine theta. And if you distribute this through, you end up with, I do move the p in to the expression here. So we get 2p cos theta r hat plus, sorry, this should be an r hat here, plus p cos theta r hat, because the signs cancel on the denominator and numerator there, so this, you just get the cosine and theta term, and then you get minus p sine theta over sine theta, so the signs also cancel there, so you're just going to minus p, and I keep forgetting my vectors. So you end up with this expression when you plug in this expression for theta hat. So this is going to be 2p cosine theta r hat plus p cosine theta r hat. So that's just going to be 3p cosine theta r hat minus p. Of course, I've just left the 1 over 4 pi epsilon naughts out front. We haven't really touched those. And then what you can do is notice that p cosine of theta, that's just p dot r hat. And that's what we want to get. That's the form of the expression we want to get. Sorry, I'm like not in the right place in the book anymore. But if you look at the expression we're trying to get, and I left out the 3. There's a 3 there. If you look at the expression we're trying to get, and I also left out the r cubed. So let me just like throw in an r cubed. So there is an r cubed here. It's been here the whole time. I'm just forgetting to add it. I left it out somewhere. Yeah, okay, starting there. So this 1 over r cubed, 4 pi epsilon naught, that's just been there the whole time. And then, yeah, this expression in here, that if you just notice that p cosine theta is the same as our p dot r hat here, then we can just plug that in. And so that gets us our expression, 3 times p dot r hat minus p. And that gets us to this coordinate free form here for the dipole, the electric field of a dipole. All right, that was a lot of weird math manipulation. I honestly don't know how you could really, this is a really hard thing to figure out. I don't know what would prompt you to be like, oh, let's just try to find an expression for theta hat here. This is kind of the key step here, is somehow figuring this out. So it's definitely a tough problem. I imagine if you kind of just have to play around with the math for a while and see if you can figure something out. But given that you have the starting point, and you could maybe do this working backwards. You could start from maybe the end expression and see if you can derive the starting expression too. That's one way to do it as well, I guess. But anyways, if you guys enjoyed this video, feel free to leave a comment, subscribe if you haven't, leave a like on the video. Otherwise, you can also support my channel via the Patreon link or the Buy Me a Coffee link down below. And yeah, I will see you guys on the next video.